Okay, so let's do a problem where we find the usual suspects, the critical points, the intervals of increase, decrease, concave up, concave down, local extrema, inflection points, and I've added in here asymptotes because that's going to be an issue. We're going to use those, we're going to find all of those and use the results to sketch sketch a graph of the function. Um, in this case, I don't want us to waste a lot of time finding the derivatives. I know that you know how to find derivatives using the quotient, using the chain rule. You can actually, the chain rule and the quotient rule are needed here. So I'm just going to give you the derivatives because the point here is not to find the derivatives but to be able to interpret them. So let's get started. Critical points. Critical points are going to be the places on the graph of x where places within the domain of x, so on the graph of x, where the first derivative is either zero or undefined. Let's look at the first derivative. Highlighted actually. There's the first derivative. So we can see that among the various components of this expression, e to the anything never is zero. There's nothing you can plug in to an exponential function that makes it zero. Negative 2 is obviously never going to be 0. X squared can be 0, but it's in the denominator, so that would make the function that would make f prime undefined. Now, you might be surprised to learn, and you could certainly be forgiven for saying, well, therefore x equals 0 must be a critical point because the derivative is undefined. But one of the reasons I put this in here is to demonstrate a point, a little remembered point about the definition of a critical point. It has to be a point in the domain of the function. Now, while it is true that f prime is undefined at x equals 0, so is f. The original function f has x in the denominator of the exponent, so you still can't plug in 0. So 0 is still not in the domain. All this to say that there are no critical points. Okay, now let's look where the graph is increasing and where it's decreasing. It turns out that this graph is actually decreasing everywhere. You can see that just by looking at what's being multiplied and divided in f prime. X squared is always going to be positive, except at 0, which is not part of the graph at all. E to the 2 over x is always going to be positive because if I take e and raise it to anything, I get a positive number. Negative 2 is always going to be negative, which means that f prime is actually negative everywhere. So that means that f is decreasing everywhere that it's defined because its derivative is negative everywhere. So we can say that it is the intervals of increase are none. The intervals of decrease are negative infinity to 0 and 0 to infinity. We have to write it that way because we're not including 0. Um, some people will write a union. A union is technically not right, although I think that MyLab accepts it in between these intervals. The reason is that if I said that it was decreasing on the entire, if it was decreasing on the union of these two intervals, what I would mean is that every point to the right has a lower x value than every point to the left. It will turn out to be the case that this is more like it's decreasing here and then it's decreasing there. But it's not the case, for example, that this is higher than this just because it's to the left. So that's why I really have to treat them separately. These are just two separate intervals on which the function is decreasing, but not decreasing on the combined union of them. So anyway, those are the intervals of decrease. Let's see, intervals where the function is concave up and concave down. So we look at f double prime, which is going to tell us which is going to tell us through whether it's positive or negative where the original function is concave up or down. What we can see is that 4 is always positive, e to the 2 over x is always positive, x to the fourth is always positive. The only thing that can be negative is 1 plus x, which is going to be negative. It will be negative if x is less than negative 1 and positive if x is greater than negative 1. So we can say is that function is concave up on the interval negative 1 to infinity, and it's concave down. It might be tempting just to look at this function and say that the answer is negative infinity to negative 1. Sorry. Actually, sorry, I made a mistake here. This was the point I was trying to make. This is actually going to be concave up on -1 to 0 and 0 to infinity. This is the point I thought I was going to make with the concave down part. The point is that it would probably be, as I did, it would probably seem, is that correct? Yes. It would probably seem reasonable just to write -1 to infinity. But the thing is that I have to exclude 0 from these intervals because it's not part of the domain. So this is the correct set of intervals on which the function is concave up, and it's going to be concave down on the interval -infinity to -1. Okay, so we have those intervals. We know that there are no local extrema. How do we know that? We know it because there are no critical points, and we have this other theorem that says that local extrema can only occur at critical points. So if we don't have any, we don't have to apply any of these tests and ask whether there's a local extremum. We also notice that the function is decreasing everywhere it's defined, so it never turns around. It can't really have any local extrema. Does it have any inflection points? The answer is yes, it does. So we can see is that the function is concave down on the interval. We'll just graph this on a number line. Put the -1 here. We can see that the function is concave down on the interval -infinity to -1, and then it turns concave up on the interval -1 to 0, and then it stays concave up above 0. So we can see that at this point the function is defined and it changes concavity. So that's an inflection point where f prime changes from negative to positive or positive to negative. So we have an inflection point at x equals -1. Okay, so last thing we want to do, since asymptotes are an issue here, is we want to put in the asymptotes. That's going to help us graph. So recall that f of x is equal to e to the 2 over x. So we want to find the horizontal asymptotes. Recall that the horizontal asymptotes are y equals the limit as x approaches positive infinity, and the limit as x approaches negative infinity. So we're going to calculate both of those limits. The limit as x approaches positive infinity of e to the 2 over x is equal to e to the 2, I'm just doing this in a very imprecise way. This is e to the 2 over infinity, which is e to the 0, which is 1. And we can also see that the limit as x approaches negative infinity of e to the 2 over x is equal to e to the 2 over negative infinity, which is also e to the 0, which is 1. So that gives us, so that means that y equals 1 is a horizontal asymptote. So we have horizontal asymptote is y equals 1. Now, for a vertical asymptote, we're looking for places where the function is undefined, and we want to evaluate its behavior as we approach those points where the function is undefined from both the right and the left. I'm going to do the left first, so let's analyze for vertical asymptotes. Not writing that very neatly, but hopefully you know what I'm saying here. So what I want to do is see that this function is undefined at x equals 0. So I want to find the limit as x approaches 0 minus of e to the 2 over x. What we can see is that as x approaches 0 from the minus side, this exponent is going to become negative infinity. We know that 2 over 0 is undefined. It's going to approach one of the infinities. But since we're approaching 0 from the minus side, that means we're approaching from values that look like -1, -0.1. Here we'll put -0.00001 just to make the point. In other words, we've got very small but negative values. So even though the smallness ends up overwhelming this function, making it infinity, it never changes its sign, sign, so it stays very negative. So this really is sort of like e to the negative infinity, which is equal to 0. All right, so that doesn't give us a vertical asymptote, but let's do this one. The limit as x approaches 0 plus of e to the 2 over x. Now we're approaching from this side where gets small but stays positive. So this is now going to be equal, this is like 2 over 0, but where it's like things that are a little tiny bit more than 0, so they're positive. So this is going to be e to the positive infinity, which is infinity. This is the mark of a vertical asymptote, is when I approach a finite point and I get either positive or negative infinity. So we can say that there is a vertical asymptote at x equals 0, because as I approach 0 from one of the sides, I get one of the infinities. So we're now ready to graph the function. The relevant parts are, we know where the function is concave up, where it's concave down. We know it's decreasing everywhere, and it has no local extrema. It has a horizontal asymptote at y equals 1 and a vertical asymptote at 0. So let's use those facts. So first of all, that's x, that's y. Actually, let's put it in a different color. Let's put in the horizontal asymptote, y equals 1, and we also have a vertical asymptote. I'm just putting it right alongside the y-axis. That line is x equals 0, which is the y-axis, but that's now I'm marking it as an asymptote. So what we can see is, for one thing, we have a horizontal asymptote at y equals 1, and we saw that regardless of whether we were approaching positive or negative infinity, the function approaches that. So we'll see that the function comes down from here. Now what's going on? What am I marking? The limit as x approaches 0 from the positive side was positive infinity, which means that as I start going towards 0 from this side, I expect the function to go way, way up like that. So that's its vertical asymptote. Now, let's look at concavity. The function is concave up on the interval from 0 to infinity. So what I want is for the shape of the graph to kind of smile upward like that as it approaches this horizontal asymptote. So that's what the function is doing there. It's approaching, it's sort of nestled between a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 1. Okay, now let's see what's going on on the left side of the graph. The function is concave down from negative infinity to 1, and then changes to concave up on the interval negative 1 to 0. So it has an inflection point here at negative 1. We've also seen that as x approaches 0 from the minus side, which we happen to do in the search for asymptotes, we see that the function is approaching 0. So it doesn't include that. I can't actually plug 0 into the function, but I can put like an open dot around there like that. And I know the function, by the way, is decreasing everywhere, because we found that. We found that it's decreasing everywhere. So that means this function is decreasing and concave up. So it's decreasing and concave up on the interval negative 1 to 0. And then it becomes, we see that it's concave down on the interval negative infinity to negative 1. So I want to change to the other concavity at that inflection point of negative 1. And we also saw, by the way, that as we approach negative infinity, we approach the same horizontal asymptote of 1. So here, there's my inflection point where the concavity changes, and we can see that just as how we got positive concavity there, we have positive or upward concavity there. Here we have downward concavity. Function is decreasing everywhere, just like we found. We found that it's decreasing everywhere. Let's just finally put in what we know about everything so that you can see how it fits onto this function. That's f prime, that's f double prime. So we know that f prime is negative there, and it's negative there. We see the function is going downward, and we also see that we have negative concavity here, or downward concavity, positive concavity briefly from negative 1 to 0, and then once we cross the asymptote, we get positive concavity again. That's what we found, is that it's concave up on negative 1 to 0 and 0 to infinity, concave down on negative infinity to positive infinity. So you can see, looking at f prime and f double prime, you can see that what we've drawn here does in fact meet the, it does in fact it is, sorry, rather it is consistent with what the first and second derivatives are telling us about the shape of the graph, and we've also had some asymptotes that gave us some more clues about what the graph looked like. So there's the graph of that rather unusual function. Let me just scroll up. This will help you if you want to go review the problem. Okay.